Good. So the last talk of the session is about CoqQ and quantum programs, and the speaker is Zhou. Please.
Okay. Hello, everyone. Thanks for coming. I'm going to talk about CoqQ, foundational verification of quantum programs. This is a joint work with Gilles, Pierre-Yves, Strub, Junyi Liu, and Mingsheng Ying. Quantum program languages are key element in large-scale efforts to deploy quantum computing. Examples of industry supported languages include IBM's Qiskit, Google's Cirq, and Microsoft's Q#. In spite of the benefits of quantum programming languages, writing correct quantum programs remains error-prone, not the least because quantum computation often contradicts human intuition. Deductive program verification provides a principled approach for reasoning compositionally about programs. There already exist several program logics for reasoning about quantum programs. This logic obeys the same principles as their counterparts for classical programs, yet they do not achieve similar usability and scalability. Program logics for quantum programs face two main challenges compared to classical programs. First, quantum states and assertions have a rich structure than their classical counterparts. Second, the effect of atomic instructions on quantum states is inherently non-local because these states might be entangled. This makes states much more. This makes the states well. This makes reasoning very cumbersome and error-prone. Common mean to ensure that the proofs of program correctness adhere to the program logic is to provide mechanized support for the program logic. However, when program logics are themselves very complex, this is the risk that the implementation of the program logic is itself flawed. One peeling approach is to develop verified program verifiers, that is, program verifiers which are themselves proved correct with respect to the semantics of the program. A verified program verifier consists of a program logic that proves sound from first principle. Furthermore, expressiveness, usability, and readability are important aspects to evaluating a practical verifier. There is already a large body of work in the verification of quantum programs, such as qwhile, sqir, qwhile prover, qrhl tool, qbricks, Isabel Maris Dirac, but some of them focus on circuit models using qubits as the basic quantum unit, and some of them are not foundational or not so practical. Thus, we propose CoqQ, a formally verified program verifier for high-level quantum programming language that operates over a general notion of state. It's foundational, expressive, and achieves better usability and human readability. One motivating example is the hidden subgroup problem, which arises in many settings, including integer factorization, also known as the Schur's algorithm, discrete logarithm, and graph theory. The problem is about group theory. Here, we consider the setting for finite abelian group G and use the fact that any cyclic group has a decomposition. That is, G is isomorphic to the Cartesian product of integers modulo P. Uh, let me skip the details, but just to show the algorithm here. It's only 5 lines of code and very simple. Yet none of the existing tools try to verify its correctness. Formalizing the correctness proof of this algorithm faces several technical challenges. First, it's not a qubit system. The quantum variable x models the arbitrary finite group G, and its component xi models the integer modular pi. Second, the flexibility to combine and decompose quantum variables x and its components xi. Third, local and parallel reasoning are required to efficiently derive the properties of parallel application of quantum Fourier transformation on each component xi. Finally, the proof employs several sophisticated lemmas from group theory and representation theory. To address these difficulties, CoqQ provides the support of arbitrary data type rather than only qubit, the labeled Dirac notation for efficient equational reasoning of quantum expressions in a local manner, and is built upon the state-of-the-art math library. The main components of CoqQ include the formalization of concepts and theories of abstract linear algebra based on MathComp and MathComp Analysis, the quantum framework that defines the frequently used mathematical object and proves the lemmas in quantum computation and quantum information. This makes it sufficient to describe the semantics and prove the properties of quantum programs. An implementation of labeled Dirac notation, a widely used notation for representing quantum states that significantly simplifies the equational reasoning of a quantum system. A formalization of the qwhile programming language with denotational semantics built from first principle, and a verified Hoare logic for quantum programs that support local and parallel reasoning, forward and backward reasoning, and provides a human-readable statement. Our formalization relies on the MathComp library for basic data structures such as finite sets, ordered fields, linear algebra, vector space, and big operators, and the MathComp analysis library, an ongoing attempt at providing a library for classical analysis in Coq that is compatible with objects introduced in the MathComp. We enrich the MathComp hierarchy with new types and theories, including Hilbert space, complete partial order, vector order, and topology of finite dimensional linear space over complex number. The tensor product of linear space is fundamental to quantum mechanics since it describes the composite quantum system. A novelty of our formalization is to use labels to tag subsystems and define the tensor product directly over a finitely indexed family of linear spaces. Suppose we have a composite system shown on the right. Any subsystem A can be identified by a subset of names of each atomic system. For example, S is the composite system consisting of Q12 and Q22, and T is a subsystem of Q21, Q22, Q31, and Q32. Following the postulate of quantum mechanics, the state space of any subsystem A is the tensor product of all the Hilbert space of each atomic system ranging over subset A. Instead of defining the tensor product of two linear spaces only, we define the tensor product over the subset, which naturally deals with nested tensor product. So the tensor of space is commutative and associative, since the order of elements in the set is irrelevant. For example, both HQ12 and tensor HQ22 and HQ22 tensor HQ12 provide the same state space of subsystem S, and thus they are the same. Similarly, rearranging the parentheses in HQ12 tensor HQ22 and tensor HQ32 will not change the final state space. This minimizes the need to handle the isomorphism caused by commutativity and associativity of tensor product. Dirac notation, also known as a bracket notation, is used extensively in quantum mechanics. It provides a notation that can describe all mathematical entries and operations using quantum mechanics, such as CAD for state, bra for co-state, inner product, outer product, and tensor product. And interprets these ingredients uniformly as linear operators. By this means, the Dirac notation allows to calculate over descriptions of quantum systems using basic rewriting rules of linear algebra such as linearity, associativity, and commutativity. We further use labels to tag Dirac notations with the subsystems in which they live or operate. For example, with a subscript S, These notations are states, co-states, inner product, and outer product on subsystem S. Similar to the tensor of spaces, the tensor here is also commutative and associative. For example, both of these two expressions reflect to the product states of S and Q. Another important feature is the localization. Suppose we apply a unitary transformation U on the subsystem S and consider the state evolution of the composite system ST. To model this, we need first lift US to US tensor identity on T, the operator acting on the subsystem ST, and then apply it to the state. Instead of explicitly writing out the cylindrical extensions of US, we might simply write US before the composition of the state. By identifying that US only acts on S, we write it into the right-hand side and leave psi t unchanged. If we follow the principle of localization objects as much as possible, that is, we lift the operators by tensoring the smallest identity operators to make the expression valid, then such a step can be automatically identified by the context since the lifting is unique. Here is an example that proves the fact that operating A on the first system of a maximally entangled state is same as operating the transpose of A on the second system. Thanks to the label Dirac notation, the equational reasoning is in a local manner, and we only need to find out and rearrange the state and operator that lies and acts on the same subsystem. Based on above ingredients, we formalize many concepts in quantum mechanics. First, this framework can be of independent interest for other purposes, such as building the library for quantum information theory. CoqQ implements a qwhile language in two levels. First, defines the abstract syntax and then instantiate it to a concrete syntax. The abstract syntax consists of skip, the command that's doing nothing, the initialization which resets the subsystem to a given state, the unitary transformation U on some subsystem S, the sequential composition, and the if and the while statement with a quantum measurement as a guard. For if and while statement, we first perform the quantum measurement M to subsystem S and obtain the classical output. Then we choose to execute the branch according to the classical output. Note that critical difference to the classical statement is that the measurement in the guard will change the state before executing the branch. Although the abstract syntax suffices to develop the meta theory of qwhile language, the formalization of textbook algorithms and their correctness proofs are greatly simplified by switching to a concrete syntax with support for typed variables. To instantiate a concrete syntax, we define the Hilbert space associated with a finite data type, then model the typed quantum variables for given arbitrary types rather than being limited to represent qubits, and finally model the composition of quantum variables. CoqQ also implements a program logic that is proved sound with respect to the denotational semantics of qwhile programs. Correctness is expressed using Hoare triple, where AS and BT are the pre and post conditions, and C is the program. A mild novelty of our approach is that we allow assertions to be arbitrary local linear operators rather than global observables, a subset of linear operators. This simplifies the proof rules since linear operators have better algebraic properties than observables. For example, observables are not closed on the addition and the scalar multiplication. Our approach also supports describing and calculating predicates transformations locally. The total correctness and the partial correctness are defined by the inequality between the expectation of input and output with respect to pre and post conditions. Compared to sharp logics for quantum programs, this choice is very expressive and can describe most of the linear properties of quantum states and programs. One remarkable point is that we introduce a human-readable statement, which can be read as if the input is in the state U, then after performing program C, the output is in the state V up to a global phase. Such a definition is consistent with the correctness defined above, and thus is just a syntactic sugar. The powerful proof system is implemented as lemmas in CoqQ. That is, rules are proved sound with respect to the semantics. It consists of several sets of rules inspired by previous theoretical works. The syntax-directed rules for basic constructs, the structural rules including frame rules, and the rules for parallel reasoning. The state-based rules for reasoning about state transformation, and the rules for both forward and backward reasoning with rule R inner that relate them. This makes it possible to write and prove correctness similar to textbook statement. Here is a screenshot of our formalization for hidden subgroup problem. The program is similar to the pseudocode, and the proof follow from the standard presentation in other textbook. Let me omit the details here due to the limit of time. Here is a code metric of our examples. We use CoqQ to formally prove the correctness of several well-known quantum algorithms from the literature, including the programs on circuit model and the algorithms with abstract data type. Most of the proofs are about 1 or several hundred lines of code, a reasonable length compared to the textbook, and shorter than other similar platforms for reasoning about programs, quantum programs. It's partly because CoqQ provides support to abstract data type and label Dirac notation, which frees us from matrix computation with tensor product. By employing MathComp and MathComp Analysis, we directly use some mathematical theories without redevelopment. There remains many further steps to improve CoqQ's expressiveness and usability. The first step is to introduce classical variables so to support reason about programs that mix quantum and classical computations and avoid meta-programming. Another important step is to support data structures, leveraging a recent proposal by Charles Yuan and Michael Carvin to incorporate data structures in quantum programs. Naturally, it would also be interesting to provide better support for automating recurring mundane tasks. In the long term, we would like to use CoqQ as a basis for a verified quantum software toolchain, such as a formally verified compiler from qwhile to quantum circuits. Okay, that's all. Thanks.
So, I was wondering about the kind of algorithms you mentioned. You proved something about these algorithms, but is it just correctness or also maybe complexity? Since all these algorithms are very interesting.
Yes, it's a very good question. Currently, we only support to prove the functionality, the correctness of functionality. For example, the hidden subgroup problem algorithm outputs the correct state, but haven't have the component to reason about like complexity or other properties. But it's really but it's a really interesting task, and maybe we can make a plan to implement this later. Yeah, thanks.
Yeah, there is a classic way to reason about the complexity of imperative programs with OR logic, which is like just instrumenting the code with a counter, right?
Yeah.
And just prove something about the value of the counter at the end of the computation. So I'm wondering whether, the fact that you work with quantum programs means that you can't do that. My guess is that you can, but can you say something about that?
Well, sorry if I understand correctly, you mean that like prove some algorithms to prove the correctness, we need to also reason about the complexity, or
Yes. But you can do that with just a counter, right? An integer variable that you increase whenever you do a significant operation, right? And
yeah.
so you could do that to reason about the complexity. This is my guess.
Yes, I think so. Yeah, but currently we haven't do this, and maybe we can do this later. And I know that there are works on like reason about the complexity of quantum programs, and they also set up like logics and other things. And we think our mathematical framework is sufficient to implement this. Yeah.
Thank you. Other questions? If not, let's thank the speaker.